Lesson 3 is about solving multi-step equations. This time we're going to be using two or more transformations. So in example 1, it says solving a linear equation, and you'll notice that we have a fraction coefficient to begin with, and we also have a constant term. We want to get both of our constant terms on the same side of the equal sign so that we can isolate our variable. So to do that, let me go ahead and undo my labeling so that doesn't get cause any confusion. So to do that, I want to subtract 6 from the left side, and staying with a balanced equation, I would need to subtract 6 from the right side. Remember to do your equal sign because you are doing a computation. The 6's would cancel out here, leaving me with 1/3 x, and that is going to equal negative plus a negative gives me a negative 14. Now, because my coefficient is a fraction means division, I'm going to do the opposite operation, and instead of dividing by 3, I'm going to multiply by 3. When I reduce, that would leave me with just 1x. And I need to do the same thing on this side to keep it a balanced equation. So negative 14 times 3 is going to give me negative 42. So my answer on the first example would be x equals a negative 42. So this time I need to, in example 2, I have a little bit more complex equation to start with. And so we're going to solve. First of all, let's point out that these are equations, not expressions that we're dealing with now. Equations have an equal sign, so we need to solve for our variable. So the first thing I need to do is combine like terms, always the first step. So 7x minus 3x is going to give me 4x, and then I'm going to copy down the rest of the equation as stated. Second step would be to isolate or get my variable by itself. I'm going to do that by adding 8. I need to add 8 to both sides, a large equal sign, the computation one. I end up with 4x on the left side of the equal sign, and I end up with 32 on the right. Now I don't want to know what 4x is equal to. I want to go ahead and solve that for a single variable. So I'm going to divide by 4, and again, doing it on both sides, balanced equation, and I'm going to end up with x equals 8 when I reduce 32 over 4. In example 3, we're going to talk about using the distributive property. So we're kind of putting everything together here. Sorry, whoops. Having some trouble turning my page. There we go. So the first step now is I need to distribute. So I'm going to go ahead, and the 5x is going up. Again, I get a different color. I don't know how that keeps happening. It's a pretty color. 5x plus 3x, a positive 3x times x would be a positive 3x. And then that same 3, positive 3 multiplied or distributed to a positive 4 gives me a positive 12 equals 28. Now I'm going to go what I learned in the previous example, and I'm going to combine terms. So I'm going to end up here with an 8x plus 12 equals 28. Now we want the variable by itself, so I'm going to subtract 12. I need to do that on both sides. That's a balanced equation. I end up with 8x equals 16. I need to divide to solve for a single variable. You'll notice I'm repeating the same kind of vocabulary, same kind of process, and x equals 2. This process will carry you all the way through the rest of the year of algebra. And near miss again, whoops. Okay. Apparently, if I hit one of my tools, I'm getting to a little lighter. I'm not sure where we'll get to this time. This time, again, I have a quantity in the parentheses, So I need to be doing some distributing first. So I'm going to go ahead and I'm going to copy my 4x. Same thing I did on the last screen. However, this time my distributing value is a -3. So -3, remember this is the whole term here, -3 times x would give me a -3x, and -3 times a -2 would give me a positive, oh that's sloppy there, positive 6. Again, let's repeat the things that we've learned in this lesson. Let's combine terms. 4x minus 3x is going to leave me with just x, which is nice. I have x plus 6 equals 21. Now I want to get solve for a single variable. So I'm going to subtract 6 from both sides. And this time we end up with a single variable, x. And x is equal to 15. Now again, you can always substitute back in. I would strongly suggest that if it's a quiz or a test, plugging that value back in and seeing if it makes a true statement. Following, of course, your order of operation rules. I have that just a little bit high, and so I keep hitting a different tool that is not visible on your screen. All right, we want to change pages here. In example 5, we have a distributor that happens to be a fraction. So I'm going to get rid of the distributor first. So, in able to get rid of a fraction, I'm going to multiply, oh, we're back to black for some reason, by its reciprocal. So I'm going to multiply by a -5/6. Sorry, that was a pretty close call there. I'll go ahead and I'll multiply this side also by a -5/6. Now, the reciprocal, that's going to result in +1, and so I'm left with just the quantity x plus 3. Now I need to reduce here, so I can say 6 goes into 6 once, 6 goes into 66 11 times. I have -5 times 11, so I have -55. Getting a little delay in my writing, so hopefully it'll keep up with us. Now let's go ahead and continue with what we've used before this. We're going to isolate the variable or solve for a single variable. And we would get a -55 combined with a -3. So we would get a -55 equals x. And again, we're solving for it, so I can switch that to x equals a -58. Now that we've practiced the process, we're going to go ahead and move on to goal 2 of this lesson, and we're going to talk about some known formulas. So the first one we're going to talk about is the formula that is commonly used, and again, we've changed the color of our marker, but to convert Fahrenheit to Celsius, or Celsius to Fahrenheit. So it says a body temperature of 95 degrees Fahrenheit or lower indicates that a medical condition called hypothermia. What temperature in Celsius scale may indicate hypothermia? So the Fahrenheit and Celsius scales are related by the following equation that I identified. So it says use the formula to convert the Fahrenheit to Celsius. So what we're going to do first is we're going to use this formula, and I'm going to substitute in the temperature that we're looking at. So it's going to be 95, and that equals 9/5 plus 32. Now I'm going to select all of this and scoot it over so that you can see what I'm working on. If I can get my writing there. All right, just in case we need a little bit more room. Wouldn't that be nice if you could do that on your papers at home? All right, so the first thing I want to do is, again, I have that coefficient that is a fraction. But I can go ahead and I don't have to get rid of that immediately. I can go ahead and I can get, oops, you know what? I forgot my, I'm going to actually erase that because I forgot my variable of the Celsius degree. So we'll see if I can write this just a little bit clearer than I did and leave a little bit of space. So I want that I'm going to have 95 for my Fahrenheit equals 9/5 of Celsius, which is what I'm trying to solve for, plus 32. So I'm going to go ahead and I'm going to get my variable by itself, and I'm going to subtract 32. Now again, you could do this the same way we did earlier at one of the other, and you could go ahead and get rid of the coefficient that's a fraction, but the reason we did that on the earlier one is because that was what was being distributed. So we're going to go ahead and just get our variable by itself, that variable term. So now we have that 63 equals 9/5 of our variable, which we happen to use C. And so to solve for C, I need to multiply by its reciprocal. I need to do that on both sides to keep it a balanced equation. So these are going to cancel out, leaving me with my variable by itself. And then 9 goes into 9 once. 9 goes into 63 7 times. So I have 5 times 7. So that equals 35. And that's degrees. So 35 degrees Celsius or lower may cause or may indicate hypothermia. This time we're going to use a verbal model, which is always something I kind of have a giggle about because verbal means out loud and model means something you can see. So I guess apparently you can see my out loud words here. But we'll go ahead, and the book likes to use this, so we'll go ahead and do that. They're going to tell me right here the verbal model solution. So it's going to tell me how I'm going to set this up. It says that I'm going to do the temperature inside the Earth equals the temperature at Earth's surface plus the rate of the temperature increase multiplied by depth below the surface. So we're going to look for all that information here. The temperature within Earth's crust increases about 30 degrees Celsius. So that is the rate of the temperature increase. So we're going to put our 30 in here. For each kilometer or kilometer of depth beneath the surface. If the temperature at Earth's surface is 24 degrees, so that's the temperature at the Earth's surface, at what depth, that's the part that we do not know, so we'll do that as a times D for depth. Will the temperature inside the Earth equal 114? So we just set up a variable equation here. Let's put our operational sign in here. Sorry about that. So if I was going to simplify, it would be 24 plus 30D. So let's go ahead and get our constant terms together. Subtract 24 from both sides. I sure didn't leave myself much room to work things out though. And 114 minus 24 is going to give me 90. And that's going to equal 30D. I don't want to know 30D. I want to solve for a single variable. So I'm going to divide by 30. And I apologize, I can't keep working this vertically. So we're going to reduce. And I get the D. And that is equal to 90 divided by 30 equals 3. Sorry. So the depth below the surface would be 3, and we could look back to see what kind of label we're using. We're using kilometers, so it would be 3 kilometers or kilometers. And let's see it looks like that is our last example for this lesson. So now again, these are things that you're going to be using quite a bit in algebra. So if you need to pause and listen to the reasoning behind it, please feel free to do that.